In this video, we are going to be calculating the variance and standard deviation of a population. So I've done some pre-work here, and I've already put up the formula for the standard deviation. Notation-wise, the symbol for the population standard deviation is called sigma. I say it looks kind of like a circle with a hat on top. It's just a lowercase Greek letter for S. And then here's the rest of our formula. It's the square root of the summation, right? Again, another Greek sigma, only that one's capital. It stands for either addition or summation. So we're going to be adding each value after we've subtracted the mean of the population, again denoted by mu, that value squared divided by n. So I've got a nice little way using a chart that will help you calculate this rather quickly. So I have an example here. Suppose a population consists of the values 5, 7, 12, and 16 that we're going to be using here. Based on our order of operations, we know that we need to do what's inside the parentheses first. And unfortunately, we do see that value of mu in there. So as a little aside, I'm going to take a minute and calculate the value of the population mean. We should already know that to find the value of the population mean, we simply add up all the values and divide by the number of values. So 5 plus 7 plus 12 plus 16 turns out that that is equal to 40. We have 4 values, and so the value of my mean is actually going to be 10. So here comes my handy little table that I can use that'll walk me through this example. I'm going to start just by taking my 4 values, and instead of leaving them in row form, I'm going to put them in a column. So I'm literally just recopying these 4 values into a column. So now inside the parentheses, I have x minus mu. These are called deviations from the mean. It's going to tell us how far each one of these data points is from that mean. So following my formula, I'm going to take 5 minus 10, which gives me negative 5. I'm going to take 7 minus 10, which gives me negative 3. And I'm going to keep going. 12 minus 10 gives me 2. 16 minus 10 gives me 6. One nice thing about the deviations from the mean is that they should always add up to 0. So we have kind of this safety net that we can use, and we can stop and say, are we doing this correctly? And if you notice in this case, my 2 positive numbers add up to 8. My 2 negative numbers add up to negative 8. So a positive 8 and a negative 8, sure enough, does add up to 0. If you had a lot of decimal places, this turned out nice because I ensured that it turned out nice. But if you have an example that maybe has decimal places and you're subtracting decimal places and you're adding a bunch of decimal places, this may end up to be something close to 0, which that's fine if you're using decimals. So either something exactly 0 or close to 0 with those decimals. So again, going back up to my formula, I have what's inside the parentheses. Now I need to go outside, and what I'm going to do is now find the squared deviations. So those 4 values that I just calculated, I am now going to square. One word of caution is that whenever we square a number, whether it's positive or negative, we always want to make sure that the answer of it squared is always positive. So these 2 negative numbers, when I square them, should end up being positive. So if I keep going, 2 squared is going to give me 4, and 6 squared is going to give me 36. So I've now done inside the parentheses, I've done outside the parentheses. The last step for the numerator is actually just to add what we just did. So I'm going to take this final column here, 25 plus 9 plus 4 plus 36. If I add that all together, it turns out I get 74, and that's actually our numerator in this formula. So I have 74 divided by, again, referencing my formula, n is just equal to the number of values. And so in this case, I've already determined that I have 4 values. So I'm going to plug that into the formula. If you want, although most calculators will do this step for you if you put it in all at once, but if you want, you can clean up that fraction. 74 divided by 4 is actually 18.5. And then the last step in my formula is just to take the square root, which is going to give me 4.3011. And there's actually a lot of decimals. Most graphing calculators or even scientific calculators will give you 8 or 9 decimal places. So we have to look at what our rounding rules would tell us to do. In this case, our rounding rules say use 1 more decimal place than what your original data contained. My original data was all whole numbers, so 1 more decimal than that would be just 1 decimal place. So my answer in this case for the standard deviation would be sigma is equal to 4.3. But that only gives us half of this, right? That gives us the standard deviation. What about the variance? I didn't put a formula down, but the formula comes directly from its symbol. So the symbol for the population variance is a sigma squared. So how am I going to calculate the variance? Well, if you notice, the symbol for the population standard deviation was sigma. The symbol for the population variance is sigma squared. Therefore, all I'm going to do is square the standard deviation. So I do want to be careful here. I don't want to use just the 4.3 because remember I rounded that. You always want to use as many decimal places as you have and only round at your final calculation. So I would actually need to take the 4.3011 and all those decimal places and square it, and it actually comes back to give me 18.5, which if you notice is this value right here, the one right before we took the square root. So the standard deviation is with the square root. The variance is the step before, right before we take that square root. So again, this was a nice quick by hand calculation of how to find the variance in the standard deviation of a population.